Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
That's good. Maybe lots of them have exams. You guys have midterms? Yeah. Having midterm is a nightmare. Okay, so today I was thinking to talk about the homework, but I figured not much student will be coming because it's right before the mid-break. I'll talk about the assignment maybe when you come back. What I want to talk about today is to have another look at this variance decomposition and see how actually it applies not only to the equity markets, but also applies to the interest rate. Okay, so let me start. So the first part of the data we use is what we are already seeing in the lecture, the industrial portfolios, right? So this is the same as what you have in the lecture notes. Light. Where is the light? Is the light controlled here? No. Yeah, I don't see any control lights here. Yeah, this is different from the lecture theater in the CBE, I think. Maybe. Oh, okay. Yeah, it says on here. Sorry, I can't control it. All right, so this was the industrial portfolio we have, right? And I also have this factors, especially the market returns. Okay, so the first question is, let me review how did we actually estimate the variance covariance matrix. So variance covariance in population can happen at any time, right? So for example, I can ask you, what is the variance covariance of industry, agriculture, food, and soda in this month? Right? This is something conceptually exists, but you don't know how to estimate it now, right? Because with just this month's returns, we can't really estimate. Right, so at any point of time, you can have variance covariance matrix between the assets, right? But we can't really estimate with just any point of time data. What we can do is to use the historical data to actually estimate the variance covariance matrix. Right, so the same as the mean. So let's say I want to estimate the first three industry, agriculture, food, and soda. So I take X to be the value of these three columns, right? So by definition of calculating the variance covariance, I can take the mean of this X, right? So you have basically R minus expected R, and then with this R minus expected R, you take R prime times R divided by T, basically, right? So that's the definition. Basically, that's what we give you the sum of X minus X, X1 minus X bar 1 square plus X2 minus X bar 2 square, etc. Right? But in matrix form, it's just X prime X divided by N. But as estimation divided by N, or divided actually by T, because we have T periods here, divided by T is not very important, right? Because T is like a fixed number. So what you're really driving this variance covariance matrix is the matrix of X prime X. Okay? So as you can see here, we can just derive it using our matrix algebra. You can also check just with the NumPy covariance function. Right? So if you compare the top matrix and the down table or matrix here, these numbers are the same, right? Which sort of confirm to us the way we calculate various covariance matrix using the historical returns is the valid method. So the thing get out of this is the sample estimate for the variance covariance matrix is X prime X divided by some fixed number of observations. Right. Now let's use this to the factor structure we talked about. So in the class we talked about this multi-factor structure, right? So X RIT, any return I minus RF, that's excess return equals to AI, which is expected excess return, right? We know that's equal to beta times lambda, right? Plus sum of all those beta loadings times the deviation of the factor, F tilde K, plus some random error. So with this structure, we know the random errors, epsilon, they are not correlated with each other across the stock. We know expectation of F equal to 0, and we know the F tilde and the epsilon themselves are not correlated. So that was the structure we started with in the multi-factor structure model. Right. So we can write this in terms of expectations, the return in excess of expectations, right? Remember, this AI is just expected return, right? So if I move AI to the left, RF canceled out. So what I get is RIT minus expect RIT, right? And the right-hand side is still there. Or in matrix form, I have this vector of excess return, which is n by 1, equals to vector of beta, which is n by k, n assets, k factor, times this vector of f to the t, plus the error term. And this is true for any of the t. Right? So for any point in time, we have this excess return of n of the assets equal to basically vector beta times the vector f, which is just sum of the beta I times fi. Right. So that's what we start with. Right. So what we want to see is what the variance covariance structure looks like given this factor structure. Right, so easily we can just calculate variance of the RT for any point in time. Right? As we said, we can just take the estimation, which is expected deviation from the mean times the vector prime of the deviation of the mean. Right, so that was in matrix form the x prime x we talked about. Okay. Now, if we just plug in this R minus expected RT with the factor structure we have, what we have is two parts, right? One part is that's correlated with the factor deviation. The other part is the idiosyncratic part. All right. So we know expected f to the t prime that can be written as matrix omega f, and expected epsilon t prime that can be written as the idiosyncratic matrix. So we also know this omega, the idiosyncratic part, is like diagonal matrix, right? Because they are not correlated with each other. And this will equal to just the variance covariance matrix of our terms, right? So you can get this theta by x prime x divided by t as an estimate. All right, so let's first consider this special case of k equal to n, which means you have as many factors as number of assets. All right, so if you have as many factors as the number of assets, then there's no idiosyncratic part. The omega equal to 0. So the variance covariance matrix can be exactly decomposited. All right. So if we further normalize this deviation of the f tilde to have the variance of 1, then this f tilde t times f tilde t prime will just be an identity matrix because the variance equal to 1, right? And it's only on the diagonals. So in that situation, the variance of the RT is really easy. It's just beta times beta prime, right? Because this is the identity matrix in the middle, and that's 0. So we can easily, calculate beta from there. Right. So if this is indeed true, k equal to n, then we can actually solve for f tilde because, this variance is just beta times beta prime. How do we solve for f tilde? Because we know, if you look at this equation, right? If we don't have error, right, or this becomes exact form, and we know the excess return here, we know we have n equation of this, right? We know beta, so we can just solve for n of the f, So this will give us exact solution for f. Right. So what the beta is? In that situation, we know if we set beta equal to square root lambda times this vector v, we don't know what v is, but if we plug in this definition of the beta to here, beta times beta prime, what you get is just this form where you have Q. Q is a matrix that has in each column the vector vi, right? And the lambda is this diagonal matrix, and in each diagonal you have this small lambda I. And we know this beta times beta prime is just sigma. Right, so the covariance matrix can be indeed decomposed into this form if we set beta equal to square root lambda vi. So we also know this in this definition, the lambda i's are eigenvalues and the vi's are eigenvectors. So this is how we can do the exact eigenvector decomposition, and to get exactly this form of the vector structure. Right, so in this vector structure, we know the total variance is just the variance of each component that can be explained by the factor f. Right, so that's the k equal to n case. What if k is less than n, which is the general case we have, right? So we also want to find the expression for f tilde. And this f tilde will be some vector times this rt minus expect rt. How do I know that? That's coming from this equation, right? So we want to solve for this. But the problem is this may not be solvable, or this actually has multiple solutions. Well, if k is less than n, we know this actually has multiple solutions, which is up to some rotation. I won't actually really talk about the details in mathematics. But what we want to solve is some f that can explain the most of the variations in the variance covariance matrix. Right, so the biggest variation in f that in that variance covariance structure. So what we can do is to just maximize the variance of this f tilde, which is v prime k times rt minus expect rt. And we know that this is just v prime k times this sigma, which is variance of rt minus expect rt times the vk. Right? And let's put a constraint that the variance of the vk equal to 1. The length of vk equal to 1. Why do I need that? Because we know this is like multiple solutions, right? So we don't want any vector that can be, very huge in length. So we just constrain the length of the vector and see how much variation actually it can explain. Okay, so once we set this up, we can just set up the Lagrangian as we did before, right? So this is just standard Lagrangian. And if you take the derivative with respect to vk, so again, this becomes 2 times some sigma vk. This becomes 2 times the lambda vk. 2 canceled out. So we have this first order condition, which it can be also written as sigma vk equal to lambda k vk. So this first order condition is coming from our desire to maximize the part that can be explained mostly, or the most of the variation in the f tilde, but explained mostly by the factor. Right, so the fact that is we have this variance covariance structure, but we don't really know factor. Okay, so we want to extract the factor that can mostly explain the variance covariance. And as you can see that this first order condition is just the definition of the eigenvector. All right, so remember in the lecture last week also we talked about the eigenvector definition is just any matrix times this vector equals to this number lambda k times the vector itself. All right, so we can just choose the solution for the first factor as when the lambda is as big as possible. Right? Now, second solution, we also need to maximize it. Then, in addition to this condition, we also want the second vector to be independent of the first vector. So you have this additional constraint here. Then you can still get this first order condition. I won't go into the mathematical derivations. So the purpose here is to show you the eigenvector decomposition is really coming from the desire to maximize the variance explained by the factor, given that we have this factor structure model as the multi-factor model, although we don't really know what the factor is. Okay. So now with this, let's look at our data. So here I want to scale the data first to be zero mean and univariance. And then I just put it to the principal component analysis with k equal to 3. And then I get this transform the data of this scale data to be in the principal component, which is, we'll see later, is really the factors. All right, so the eigenvector is this components dot transpose. That's the eigenvector, that's the V. As we talked about in the lecture, the eigenvector just gives us the weight of each asset to get to the factors, right? So if I just define this weight to be the eigenvector divided by the sum of each eigenvector, that will give me the weight that I need to actually get the factor terms. So this is also called the mimicking portfolios. All right, so if you look at this, for example, for the first factor, you notice this is almost like equally weighted. Right? Remember, we have industry portfolios. So if you put about less than 2% in each of the industries, remember we have 49 industries, so it's about 50. So 100 divided by 50, that's about 2. So each industry will have about 2%. Right? So each industry, about 2% will give us the first factor. And as I show you in the lecture, this is first factor is really closely related with the market returns. Well, we can calculate, once we get weight, right? We can calculate the factor returns. The factor return is just the weight times the n of the returns in time t. Right, so for here, I have this x, which is the return of the industries, matrix multiply with this weight w. So I have this factor returns here, f1, f2, f3. So if you look at this f1, This is like negative 7.8%, positive 6.5, almost 0, positive 0.8. And if you compare this to the market returns or the market access returns, they are actually quite close. Right. So that's one way to actually get the factor returns. Another way to get the factor returns, as we talked about, is just take this PCA projection. Right. So this is really x times the eigenvector, right? So in lecture notes, we have this x times the q of k, right? So q of k is the k columns of the first k eigenvectors. This is also a way to get the factor returns. Right, so if I plot both the f I just calculated and this xPCA, I can calculate from x times q of k against the market return. What do you notice here? They are the same. Except if you look at the bottom scale, in scales they are different, right? But in terms of the correlation structure, they are the same, right? But when we talked about the factor returns, all we really care about is the fluctuations, okay? We don't really care about the scale or the levels, right? So that means both approach will get us correct factor fluctuation or factor returns, or f tilde of the t. Okay, so both approach really are the same, and they are both they are actually correlated with just the first factor market return. Remember, we also have this definition of beta I equals to square root lambda times VI. Remember at the beginning when we derive things, right? If you just go a couple slides back. But when I derive that, I don't really know what this lambda is, what this V is. But we just show you this lambda is just the eigenvector, this V is, lambda is just eigenvalue, V is just eigenvector, so that we can actually calculate the loading beta directly from them, right? So in this program, the lambda is in explain the variance, right? So I take the square root of this array and then take the first element from it. And V is in this components dot transpose. And I got the first vector, so all the rows and the first column, so the first vector of it will just give me V. Right, so in that sense, I can actually calculate what the beta is. So this is the first beta, basically, beta 0. Right, so again, what should be the interpretation of this beta 0? Beta is what we call what? Loading, right? So this beta on the first factor that we extract, that'll be the loading on what? The first factor is really close to market returns, right? So this beta will be the loading on the market returns. And if you count, there's 49 of them. That's 49 industries, right? So 49 industries each have loadings on the market returns. Okay, so for example, the first one I remember is agriculture. I think the third one's food, right? So these have like low loadings, and some of these have high loadings. Right, so each industry have different loadings. So that's one other way to actually calculate the loading directly from the variance covariance matrix. The variance covariance matrix and the eigenvalue and the vector of it. Well, this suggests another way actually to extract the factor returns. Anyone know how to do the factor returns? If we know beta, how do we estimate the factor returns if we know beta? So remember in Farmer-Macbeth's approach, right? You run time series to get the estimate for beta. Then you run things cross-sectionally to get the estimate for risk premium or factor returns, right? So if I know beta, I can just run the regression cross-sectionally. What we get will be the factor return, and I can do this period by period, right? Or I can just put them all together. So this is to estimate all the betas the same time with the matrix algebra. So you have beta 1, beta 2, beta 3. And with this beta 1, beta 2, beta 3, I can just estimate the factor returns from this beta. If I put everything together, estimate simultaneously, because each epsilon have different variance, right? So this has heteroscedasticity. So instead of OLS, we can use the GLS to estimate this factor returns. But I'm not going to get into details about that because you need to, know statistics, how to calculate the GLS, things like that. But if you're interested, it's basically putting this omega inverse into the x prime x, x prime y. So instead of x prime x, x prime y as the beta estimates for OLS, you'll have x prime omega inverse x times x prime omega inverse y. So it's weighted by omega inverse. But I will skip the details about this. Right, so anyway, so another approach is we can extract the factor returns by first estimating the beta, then use the cross-sectional regression to estimate the factor returns. So that's how you can actually use some of the statistical technique to estimate the factors. As we said, how many number of factors to put in is an empirical question. Right? If you look at the mean square error of putting in increasing number of factors, the mean square error drops dramatically when you put in the first factor, which is the market, then drop in a little bit more when you put second and the third. Second and third almost have the flat MSE line. And then When you put more, it drops much less, right? So there's ways you can put in some penalty function for increasing number of the factors to get the optimal number. But that's probably for some PhD students. I don't want to talk in detail here. What I do want to talk about is to show you this factor structure is not only for stocks or equities, it can be also used for the interest rate or yields. Okay? So what I have here is the yield structure or yields in different time periods and in different durations. Right, so M1, that's 1 month, 3 months, 6 months, 9 months, 12 months, etc. And up to 10 years, 120 months. Right? So first of all, as I talk to you on Monday, right, you can get the average yield curve. Average yield curve is upward sloping, right? So on average, with the longer term, the yield is higher, right? So this is the average, but that's not true all the time, right? If you look at this yield plot, what can you see here? So for example, in the late 1970 and early 1980, you have this blue line, which is a 3 months yield, much higher than this brown line, red-brown line. Red-brown line is the 10-year yield, right? So in those periods, the short-term yield actually is higher than long-term yield. So you have the flip of the yield curve, right? Usually, as I told you, this is in the period of recessions. You can also get the newest data, look at the yield during 2008, 2009. That's also flipped, right? So that's the first thing to observe. Most of the time, the yield actually, the blue line is below the red line, but sometimes the blue line actually is close or even higher than the red line. The second thing to observe is these three curves, which is like 3 months, that's 5 year, that's 10 year. These yields go mostly together, right? But sometimes the difference is wide, sometimes the difference becomes smaller. If you look at the correlation structure of them, what do you observe here? What can you observe by reading this table? A decrease. So how do we say it? Right. So if you look at 10 years, look at this corner. This is also very big. Right, so it's not just as you go to longer term, it decreases. Right, so in this corner, right up corner and the left downward corner, number is smaller. In the left up corner and the right down corner, the number is bigger. Right? So what does that mean? That means the yields of similar terms, of similar durations, they are more correlated, right? And the yields of different durations, they are less correlated. M1 and M120, they are less correlated, right? M120 and M108, they are also highly correlated. So long yields correlated with long yields, short yields correlated with short yields, but long yields and short yields are not very correlated, or less correlated, right? So this actually suggests there are actually some structure in this yields. Let's do a standard decomposition, right? Let's say I want 3 factors, and I want this PCA transform to be fitting these 3 factors. All right? Let me first look at the eigenvector. So this is components 0, which means the first eigenvector. What can you observe? They are all like 0 to something, right? Remember, the eigenvector, each of the components in the eigenvector is like weight in your mimicking portfolio, right? So that means if I were to mimic the first vector in this yield structure, I need to put almost equally weight on the different periods of the yields or interest rates. Okay? So that's why this first vector is sometimes called the level vector by people. Why it's called the level vector? Because this is applied equally to the short rates and to the long rates. Okay, so short and the long rates will both increase or both decrease almost the same when this factor changes. Okay, so that's the first thing we can observe. In fact, if I put all the factors when we get from this XPCA, the projection for the first 3, I can call first one the level factor, the second one the slope factor, the third one the curvature factor. You will see why I call that just in a second. All right? So, but the first thing observe is dimension is still T times the number of factors, right? Because if I have transformed the thing to the PCA space, the XPCA is just X times the Q of K. That'll give me T times the K of the factors. Okay? So, first of all, let me run some simple regression. If I run 6 months return to the level, slope, curvature, it's loaded positively on level, positively on slope, negatively on curvature. I can do it for the 5-year interest rate or 5-year yield. By the way, these are treasury bond yields, right? So you can see level is still positive, but slope now is negative. Curvature is non-existent. Right, so there is something in the duration of those yields with respect to these 3 factors, okay? So if I just plot these 3 factors, so the blue is the level, right? And the level actually has big swings. Why is that? If I use the most recent data, I'm not going to observe this, by the way. Can anyone tell me what happened to the early 1980s in the US? Recession and what happened to inflation? What happened to the interest rate in the early 90s in the US? The inflation is high, By the way, who's the president? Ronald Reagan, right? Carter's late 70, Reagan's early 80, right? And Reagan has this economic policy of high interest rate to attract the capital, right? So you see this interest rate swings bigly, right? So this level just indicates the general level of the interest rate regardless of the duration of the treasury, right? Slope measures the yield slope, basically, right? So it's the relative difference between the long yield and the short yield. By the way, this slope should really be flipped. So negative slope, if you look at like early 80s, right? So if you flip this green line, you'll see in the early late 80s, this slope will be negative, which means the yield curve will be flipped in the early 80s. Right? So at the beginning, we just observe in the early 80s, you have short rates much higher than the long rates, right? So this captured by this slope curve. And the red one, the curvature curve, doesn't really move much. So to further, I can plot this M120. So this is a 10-year curve. So this is a long-term yield, right? Again, this level curve. Well, this level curve is much more volatile, but you can sort of see they are moving in the same direction. Right, so the long-term curve are actually moving with the level curve. So next graph I want to plot is to plot this flip of the slope curve with the difference between the 10-year yield and the 3-month yield. So the blue line is the difference between 10-year yield M120 with M3, the 3-month yield. And the green line is just the flip of this slope curve. Now you can really see these two things are really, really close. Right, so remember what's the slope? Slope is the second eigenvector, or the second factor we extracted from this matrix of different durations of treasury yields. Okay? So the second factor is really the difference between the long-run yields and the short-run yields and measure the slope. That's why I call it slope. I can also plot 2 times the 2-year yield minus the 10-year yield plus the 3-month yield. So if you see what I'm doing, this is like doing the quadratic functions, right? And 2 of the middle rate minus the very, very long yield plus very, very short yield. That's the curvature of the yield curve. And you can see this is really closely related to the third factor, factor dot curvature. Right, so with this return structure, we can sort of summarize all the yields from 3 months to the 10 years with just these 3 factors. And I can reproduce those curves with those 3 factors. I can predict the yield by just predicting the factors, because those factors, as you can see, has AR structures, autoregression structures, right? So, in fact, the factor structure in the yields or in the interest rates actually is much easier to interpret than the factor structure in the equities or stocks, right? We can interpret them as the level for the first factor, slope for the second factor, and the curvature for the third factor. And the top three factors actually explain the 99% of the variation of the interest rate yields. How do I know? I can look at the lambda, right? Lambda just gives me